Welcome back to Analysis for Shut-ins. Today we're going to be proving our last significant theorem about Limsups. So before we get to the theorem, I want to remind you of a couple of things that we already know. We know the definition of the Limsup. Let's remember that. The Limsup of a sequence an is the limit as cap n goes to infinity of the supremum of the tail of that sequence. So you want to think about cutting off the sequence by identifying a point cap n and then taking the tail, everything after that value cap n. Take the supremum of all of the values of the sequence in that tail, and then what you get is a single number that depends upon cap n. It depends where you cut it off. And so then you let cap n go to infinity, and you take the supremum of all of these, you take the limit of all of these suprema. So that's what the Limsup means. And we also, I want to remind you of this simple proposition. If we have a sequence an and another sequence bn, and we calculate their limits, if their limits exist, so this is assuming provided the limits exist here. Then if we have an inequality between an and bn, an less than or equal to bn, then we get the same inequality on their limits, provided that they converge. We're going to be using both of these, of course. We're going to prove today this simple theorem about what happens when you take the Limsup of a sum. Now, before we get into this theorem, the limits of sums behave nicely, and you might expect that you would get an equality here. What I want to do is I want to illustrate a reason to believe this theorem and a reason to think this theorem is strange. So first of all, we might expect an equality, and because this is because we have a general statement that says the limit of an plus bn is equal to the limit of an plus the limit of bn. And that's provided the right-hand side exists. And so we may expect that the same would be true of Limsups. But the Limsup it doesn't behave quite so nicely as the limit. It can exist even for divergent sequences. It can be based on only a subsequence of a sequence. And so you might expect a less than or equal to. But before we get into this, I want to give a very simple example of a situation where the Limsup is equal to the sum, and then another example where the Limsup is different from the sum. So let's look at a couple examples of what's really going on here. So if we let an be 1 over n and bn be minus 1 to the n, then bn will alternate and an will just decrease. If we plot this, what's going to happen is we're going to start at 1, we'll start with minus 1 and then plus 1, so we'll start with 0. And then at 2, we'll get a half, and then we'll get positive 1. So this takes us all the way up to, let's say this is 3 halves, and I suppose that puts 1 here. And then we'll get minus 1 plus a third. So that would be down to 2/3. And what will happen here is that we will oscillate back and forth and back and forth and back and forth. And you know what? I drew that kind of badly here. So we'll get an oscillatory behavior where for even terms of the subsequence, the sequence is going to be converging toward positive 1. And for odd terms of the sequence, it will be converging toward negative 1. So if we add these sequences, so this is a plot of an plus bn, we'll get this kind of weird behavior. Now, because of this subsequence, we'll get a subsequential limit equal to 1. And that will actually be the Limsup of the sum here. So the Limsup of an plus bn is going to be equal to 1, which is maybe what you would have expected here. Here, we'll also have the Limsup of an is its limit. In the case of an, the limit exists. And so that would be 0. And, well, I should have written Limsup. So the Limsup of an will be 0. And the Limsup of bn will be this is going to alternate between plus 1 and minus 1, and the Limsup will be 1. So here you see these things add up, right? 0 plus 1 gives us 1. And so this is the equality that you might expect here. But let's look at a different example. If we simply take a simpler example, if we take an to be minus 1 to the n, and bn to be the negative of that, so they're both alternating sequences, but they're kind of out of phase. When one of them is 1, then the other one is minus 1. So the Limsup of an is going to be positive 1, and the Limsup of bn is going to be +1 again. So basically, an has this subsequential limit along the even values of n, which is equal to 1, and bn has a subsequential limit along the odd values of 1, which is equal to 1. And so the lim sup of an will be 1, and the lim sup of bn will be 1, but they will always be out of phase, so that if we actually add them here, the lim sup of an plus bn, the sum of these two is actually always 0. And so this is the lim sup of the constant sequence 0, which of course is 0. And 0 is not equal to 2. So it's not equal to the sum that we might have expected if we expected this to be an equals. So basically, the way we should think about this working, an can have subsequential limits that identify their lim sup. Bn can have a subsequential limit that identifies its lim sup. But those subsequences, that subsequence of an and that subsequence of bn that identify the lim sup, well, they might not be related. They might be completely disjoint subsequences, at least disjoint collections of indices defining the subsequences. So this is a little bit of insight into what this stuff means. Let's get to the proof. We're going to prove this. So we've proven a lot about lim sups and subsequential limits, but we're going to try to prove this in as basic a way as possible by simply using the definition of the lim sup. So let's get started. The lim sup here is about the limit as cap n goes to infinity of the supremum of the tails. And so what we're going to do first is we're going to fix an n. So fix a cap n. And what we're going to do is we're going to consider the three values, the supremum of the set Sn plus Tn, where n exceeds cap n, and the supremum of Sn, oops, I wrote that wrong, the supremum of Sn, where n exceeds cap n, and this one we're going to call cap s, and the supremum of Tn, where n exceeds n, and this one we'll call t. So actually, this one should probably, if I'm going to give them names, I should probably index them with an n, because these depend on the value of cap n, right? For every different cap n, we get a different tail sequence, and we get a potentially different supremum. So let's call this cap s sub n. It's the supremum of this. We've assumed that these are bounded sequences, so we know that the supremum must exist. Now, what does it mean to be the supremum? It means that Sn is an upper bound for Sn. This cap Sn is an upper bound for all the lowercase sn. It also means that it's the smallest possible. So cap Sn is the smallest, it's the unique smallest upper bound for this set Sn where n exceeds cap n. And then I can say exactly the same thing about Tn. Tn is the smallest upper bound for the set of all Tn where n exceeds cap n. Now, if it is the smallest upper bound, then it is at least an upper bound. And so let's just say what it means for this Sn to be an upper bound of this set. That means that little s sub little n is less than or equal to cap s sub cap n for all n greater than n. And then I can say the same thing about the t's. It's for all greater than n because this set is the tails of the sequence where n is greater than n. So that means that Sn exceeds, cap Sn exceeds little sn, and cap Tn exceeds little tn. So then what can we say about Sn plus Tn? Well, I can just add these. So what we get is that little sn plus little tn is less than or equal to cap Sn plus cap Tn. So now, okay, so what? Well, I have then this inequality, and now this thing has a supremum. but we can't assume, and we're not assuming that that supremum of this is cap Sn plus cap Tn. But it must have some supremum. And the fact, well, this is actually for all n greater than n. So this thing has some supremum. What do we know about it? We know that the supremum of this set is the least of the upper bounds for this entire set. But this equation tells us that this cap Sn plus cap Tn is an upper bound for that set. So basically, I'm just going to use the definition of the supremum here. I'm going to say, look, if you have a single upper bound in your hand and you want to compare it to the supremum, you know the supremum is the smallest of the upper bounds, and so you automatically get a relationship between any known upper bound and the lowest of all upper bounds. So since the supremum, so let's write this out, of Sn plus Tn is the least upper bound of the set. And what is that set? I should have written here the supremum here where n exceeds n. It's the least upper bound of that same set where n exceeds n. The supremum of Sn plus Tn for all n exceeding cap n is less than or equal to cap Sn plus cap Tn. Now, okay, so we get an inequality between this supremum and this, which is effectively the sum of two suprema. Now, what I want to do here is recognize what these things are now functions of. So this cap Sn is the supremum of the tail cut off at the cap n location. This is not a function of little n. This is a function of cap n. It depends where you cut off this tail, but you've taken the supremum of all the little n's beyond that. So this is no longer a function of little n. This is a function of cap n. This is a function of cap n. And this too is a function of cap n. We've taken the supremum over all the little n's that exceed cap n. It depends which cap n we took, but it doesn't depend on little n. So I want you to think of everything here as a function of cap n. Now, if these are functions of cap n, then we can take their limits, and we can reason about what happens when we take their limits. When we take the limit of the left-hand side, as cap n goes to infinity, then by definition we get the Limsup. So let's take the limit of both sides of this equation, and we'll see what happens. And I seem to have plenty of room, so let's move over here. So the limit of, so let's say take limits as cap n goes to infinity, and we get the limit as cap n goes to infinity of the supremum of Sn plus Tn for n greater than cap n is less than or equal to the limit as n approaches infinity of cap s sub cap n plus cap t plus cap n, cap t sub cap n. Okay, so this is just what happens when we take the limits as n goes to infinity. And I've taken limits of an inequality here, right? I have an inequality of something depending on cap n and something else depending on cap n, and I'm taking limits and I'm asserting the same inequality for the limit. And that's basically, I've used this proposition here. By the proposition, I know that the limit obeys the same inequality as the terms. Now the terms don't, so I want to call your attention to the fact that these are sequences of little n, and these are sequences of cap n. And it doesn't matter. It doesn't matter what variable we're using to index the sequence. The basic principle is if you have a sequence indexed by some variable and you take the limit as that variable goes to infinity, then, well, the limit will obey the same inequality, the same less than or equal to inequality that the terms obey. The terms are now a function of cap n, but it doesn't matter what variable we use. It just matters that we take the limit as that variable goes to infinity, and then we get to infer the same less than or equal to relationship. So these are functions of cap n, these are functions of little n, but don't let that bother you. So by application of this proposition, we get the same inequality on the limits. Now, this is the very definition of the Limsup of Sn plus Tn. What we get here is this is Limsup Sn plus Tn. And that's the Limsup. Now we write that on little n. And this is the, what is this? This is the limit of a sum. Well, the limit of a sum is equal to the sum of the limits, provided that they both exist. So let me provisionally say that's by the sum law. But it's provisionally because like this sum law only applies when the individual limits do actually exist. And so we need to address that. But let's address that. What is this limit of Sn? It's the limit of, as cap n goes to infinity, of exactly this quantity. And so this is nothing more than the Limsup of Sn. What we get here is the Limsup of Sn plus Tn is less than or equal to, this is by definition the Limsup of the Sn, which after the fact justifies the sum law because I know that the Limsup of the Sn exists. And then this is the Limsup of the sequence little t sub little n, which is exactly what we were trying to show here. So what makes this proof somewhat challenging is that it combines the definition of the supremum with the definition of upper bounds and the behavior of upper bounds with this inequality for sequences with the sum law for limits. So all of these pieces fall into place and we get this proof.